As we look at interference, one interesting thing that is important to study in this section is path difference. Path difference will give us an indication of whether at a particular point on an interference pattern if we will have constructive or destructive interference. So here's basically how the calculations work. We had looked previously at our interference pattern, which is this big picture here on the bottom, and in the interference pattern we said there were certain nodal and antinodal lines. So the straight up the center one, that is the antinodal line, that is the zero order line. Anywhere along that line you will have a path difference of 0, meaning if I counted from source 1 to one position on the zero order line, and then I counted from source 2 to that same position, I would find that there is a 0 difference in the number of waves between S1 and S2 to that certain point. So anywhere along the zero order line will have a 0 path difference. And that's true for the other lines as well, that if you know the number for the line, so for instance the first antinodal line, you will find that anywhere along that line you will have a path difference of 1, and for the nodal lines you will have a path difference that turns out to be half numbers. So the first nodal line has a path difference of 0.5. Anywhere along here we'll have a difference of half of a wave if I count from S1 and then I count from S2. So if we look at that as a calculation, you can use this as a basic little equation and say the path difference equals m times lambda, where m gives you the number of the line, so the number of waves difference between the lines. So if it's on the first antinodal line, then m would be 1, and as I put here, the first nodal line, m would be 1/2. So that tells you how many waves difference that you have. So you can find the path difference if you know m and then the wavelength. So sometimes they'll ask you to solve for the wavelength, sometimes the path difference, usually not for m, although they can do that as well. So we're going to take a look at 2 examples as we talk about this. The first one I think is the simplest. So this example has 2 speakers that are in phase. For one thing, interference isn't something that only happens with light. Anything that has wave behavior has interference. So that's why you might see some problems that use sound or some other type of wave, but as long as you're talking about 2 sources and a wave, you can have interference. So we just look at interference in the light chapter, but it does apply to everything that's a wave. So 2 speakers are in phase. In phase just means they're played at the same time, so you don't have one turned on and then the other turned on in such a way that their waves are not in sync. So in phase mean that their waves are in sync with each other and are emitting a note of 680 hertz. One of the speakers is 5 meters from you and the other is 6.5 meters. Will you hear a loud tone or a soft tone? When they ask you that, if you're going to hear a loud tone or a soft tone, what they're asking you is, do you have constructive or destructive interference? Because if you have constructive interference, you would hear a loud tone, and if you have destructive, you would hear a soft tone. So I went ahead and wrote out our knowns here. So we know the frequency, we know the 2 paths, and we can use the speed of sound as 340 meters per second. Here I made this example so the numbers work out nice and pretty. So I use 340 here instead of sometimes I do use 345. So here's the trick. If you want to find out if you have constructive or destructive interference, you need to do 2 things. First, you need to find the wavelength, and that's easy enough given the frequency and the speed of sound. So if we find the wavelength and we know how many waves, then we can find out how many waves are in our path difference. So you can see our path difference here is 1.5 meters. So the question is, how many waves is that? If that turns out to be a whole number of waves, we'll have a loud tone, and if it's a half number of waves, we'll have a soft tone. So we'll go ahead and do the math here. So first up, we'll go ahead and find the wavelength. So this is our classic V equals F lambda equation rearranged for lambda, since that's what we're solving for. So 340 divided by 680, that conveniently comes out to be exactly 0.5 meters. So that's a nice, well, sort of even number, a nice fraction, I guess you could say. And we have the path difference here is 1.5 meters. So as I said before, and as it says in the solution there, if you know how many waves you have in that distance of 1.5 meters, you can determine whether you have constructive or destructive interference. So in this case, we have 1.5 meters, and each wave is 0.5 meters, therefore you have 3 waves. That should make sense, right? 1.5 meters, each wave is half a meter, that's 3 waves. 3 waves is a whole number. Because it's a whole number, that tells you you're going to have constructive interference, and in this case that's going to be a loud tone. If this were a light problem, you would say it's brighter, or if it were destructive interference in a light question, it would be dimmer. So in this case, 3 waves is going to be a loud tone. Instead, if the numbers had worked out in such a way that this turned out to be, say, 2.5 waves or 0.5 waves or anything that's half of a wave, that's how you would know you would have destructive interference. So that's my first path difference example. The second one I think is a tad more complicated. So the second one, I think probably the hardest thing about these problems is they're a little bit abstract. So you read the problem and it's kind of hard to picture. So we'll draw ourselves a little picture here as we go. So we have 2-point sources and they're generating periodic waves. That just means waves that have a frequency. If it has a frequency, it has a period, right? And they're in phase. Again, we're not going to deal with anything that's not, so don't panic when you see that word. A point on the third antinodal line of the wave of the pattern is 10 centimeters from one source and 8 centimeters from the other source. Construct a sketch of the situation and determine the wavelength. So first of all, here's a little sketch for us. So we've got 2 sources, source 1, source 2, and we have some point, I labeled it P. So now we don't know if P is to the right or to the left of these two, so we don't actually know if S1 or S2 is longer. They didn't label the 10 or the 8 as S1 or S2. So if you had drawn this with the P sticking out to the other side, that would be just fine. So we know there are distances that are given. So we put those on my picture. I've got 10 and 8. And that allows us to find then the difference between the two distances, which is simple enough. I just drew the black line on the picture then to show that anything past that, anything past my little black line there, is going to be 2 centimeters. So my orange dotted line represents the difference in distance between the 8 centimeter line and the 10 centimeter line. That's 2 centimeters. Another interesting thing it says in the problem, or important thing, is that it's on the third antinodal line. Any point on the third antinodal line has how many waves difference? Anybody? 3. So I know that it's 2 centimeters and that 2 centimeters is also 3 waves difference. So that's 2 important things we can get from our picture and from the problem. So m equals 3. And we're looking for lambda. So now, simple enough, if you figured that, I think the hardest thing about these is setting it up. So once you have the picture and you have your knowns, the actual math is pretty easy, but it's kind of figuring out what you're supposed to do with it to begin with. It's the hard part. So now if I go back and look for lambda, I can use my little equation and I can say that I have 2 centimeters, and in 2 centimeters I have 3 waves. So if you think about that, if you have 3 waves in 2 centimeters, how large must each one be? And so that's going to be 2 divided by 3, so that's 2/3, which is about 0.67 centimeters is going to be my wavelength for this problem. So this is how path difference problems work. They kind of are, once you get a couple of them, like these 2 examples, they don't do a lot else with them, but you do have to understand when you see one what you're supposed to do with it. So hopefully this will help you out a little bit, and we'll have practice problems that will give you a chance to look at these on your own. And that's the end of this one.